Okay, energy is the capacity to do work. This is like some of definitions. I looked at the assignments, some questions for the assignments. They cover definitions and it covers problems. The heat transfer of thermal energy between the two bodies that are different at different temperature. The flow is always from hot to cold. Temperature is the measure of the thermal energy, and it's not same as the thermal energy, but is a scale that will help us to understand or at least know the difference between hot and cold. When we study thermochemistry, we want to know if how energy is being released, energy is being absorbed, or how much of energy is being absorbed or released in a process. It could be a physical process or chemical. When the reaction or process is exothermic, is going to release heat. The temperature of the environment is going to go up. The sign for delta H for exothermic reaction is negative. For endothermic processes, the energy is being absorbed. That means if you don't provide energy, there would be no reaction or no process, no change. If you look at the reactions, for exothermic energy appears on the product side, for endothermic energy appears in the reactant side. And we talked about the delta H being positive or negative for endo and exothermic reaction. The enthalpy is the amount of the energy that is going to be transferred or is going to be released or absorbed during a reaction. So it's calculated based on energy of the product minus energy of the reactant at constant temperature. For a exothermic reaction, the heat is going to be released, but if the sample is going, let's say this is just an example, if the ice changes to water, or water from solid phase changes to liquid phase, the energy or internal energy for the liquid phase is higher than the solid phase. So this energy must be absorbed from the environment. The reaction is called endothermic reaction. The delta H, the sign for delta H is positive. Now, if we reverse this reaction, what's going to happen? The sign for the delta H is going to change also, be reversed. What does delta H negative means? It means that energy has been released. That means your product has less energy than the reactant. What does positive means? It means the product, if you look at this arrow sign, the product has more energy than the starting material. But how do we know the product has more energy? Just compare solid with liquid. In a solid phase, molecules are in rigid position. They are not moving around. They don't have energy. In liquid phase, molecules are moving around slightly, and that moving around slightly, it requires some internal energy. So if we go from liquid to gas molecule, it's going to be also endothermic, and that endothermic means that energy, a lot of energy actually in that case, is needed for liquid to change to gas, because the gas molecule by nature, they are moving around, and behavior of gas is different from behavior of the liquid molecule. Behavior of the gas molecules that they are moving constantly in random direction, they are moving in a straight line, but for something to move all the time needs a lot of energy. So going from solid to liquid is endothermic. That means it requires energy. Going from liquid to gas is endothermic, and it requires even more energy to go to the gas molecule. So sometimes it's easier to understand going from liquid to solid. Other times, when when there's a chemical reaction. So for a phase change, it's easy to understand. But if it's not a phase change, when is a chemical reaction like this, then the delta H value should be given to you for this reaction, or you must know what is the internal energy of water, what's the internal energy for CO2, and what are the internal energies for the reactants. So if we have the internal energy for reactants and products, then we can calculate the delta H, which is the energy of the product minus energy of the reactant. So let me put it this way. The sign for negative, it means that products have less energy than the reactants. So I'm just trying to cover the definitions at this point. If this value is given to you, then you know that it's coming from more stable product. So if your reactant stay in this level of the energy, products, they have less energy. The difference between the energy of the reactant to product has been released to environment, and that release of the energy to the environment appears as the delta H value. So basically, when you have the value for delta H, there are two things that is going to give to you if the reaction is going to be releasing heat or absorbing heat. The sign for is going to show you, and the value for the energy, how much energy is being released. Now, if you have a reaction that has with the known value of delta H, I already told you if you reverse it, is going to be the sign is going to change. Delta H is going to change. You need this for Hess's law because you do have some questions based on Hess's law in the exams and on the assignments. If you multiply the whole reaction by 2, basically you are going to give coefficients that represents number of mole. So this reaction H2O solid going to liquid 6.01 kilojoule. But if you use 2 moles of ice changing to water, you do need 12 kilojoules of energy. That means you are going to double the energy needed to change. Instead of 18 grams of ice to water, now you're changing 36 grams of ice to water. So basically, when you double the coefficient, that means you're doubling the number of moles. And when you double the number of moles, that means you are increasing the mass of the reactant. So those numbers, if you can make a relationship out of those numbers, is going to help you with problem solving. If you divide reaction by 2, the delta H value also is going to be divided by 2. So you have example here, how much heat is evolved when 266 grams of phosphorus is burned in the air. First of all, you have to have the delta H value because for the reaction. So this value is the kilojoule expressed, is the reaction specific. So this value is for this reaction only. So this is for the P4, and when you have no coefficient, that means is 1 mole of P4. So 1 times 31, 1 mole of P4, that is 31 times 4. That's the mole atomic mass for phosphorus times 4, basically 123.9 grams of P4. So if now we have 266 grams, first we are going to see how many moles is this. You can do that, or you can do in one step. So in the one step, you are going to, in one step, you can first change to the number of moles and say that you have the 266, it's more than about 2 moles, but you need the exact number. And since you have this value of delta H per mole, then you can divide that by the, multiply by this value to get, when you have the number of moles, because this is per mole, and you are going to get the total energy being released. So this is just the calculation for delta H value. The other definitions and the calculations that you had was for heat in a process, and the heat capacity, definition for specific heat and definition for heat capacity. A specific heat is expressed, is a definition that is going to show how much energy is needed for 1 gram only, okay, for 1 gram. And then heat capacity, it's for given quantity. So when you say calorimeter, the device or the bomb calorimeter, at that point you are using heat capacity because you don't want to have the mass of the calorimeter. You're saying that this setup, this calorimeter is going to take X number of joules of energy in order to change the temperature. But when you say specific heat, that is based on 1 gram only. Sometimes they give you specific heat. The question is asking per mole. So you use the specific heat to find the energy transferred per gram, and then you have to change that to number of moles in order to answer the question. So those are the trick for the multiple choice questions, and you have to be careful. When you are using a specific heat, you are basically using per gram. So the general formula for heat is Q, that is the mass, times the change in temperature, and times a specific heat. Now, if it's for one item, you just use that formula. If it's two mixture of two, when there's a heat transfer, then you have to use an equation. Is it okay if I log off from this and log it back to pull it in my Surface so I can write some of these problems on the board, or that would be too much of interruption for you? I don't want to get, yes, okay, because now if I only talk, it's okay to stay, or should I go to the Surface so I can write on the board? Go to the Surface. Okay, okay. Let me. That means I have to log off because it didn't allow me to join from the other one, because I have to leave. Okay, how much heat is given off when 869 gram iron bar cools from 94 to 5? So what you need to do first is going to be label what's given to you. Okay, you have to label these. So when you label this is the mass. Okay, that's the mass. Then this one is initial temperature, TI, initial temperature. This is your final temperature. And you write the formula for Q. What is the formula for Q? Equals mass times a specific heat times change in temperature. Okay, change in temperature. When you label your numbers, you have your formula. Plugging in is very easy. So you just plug in the numbers. So first of all, you need to find your delta T, and that's what is done here. You find the delta T, and then a specific heat should be given to you. If it's water, it's 4.18 joules per gram degree Celsius, or 1 calorie per gram per degree Celsius. This is for H2O. For everything else is either unknown, you need to find it out, or it should be given to you. So the problem should provide it to you. So using this formula, you have the mass you already labeled. because that's the first step. You want to make sure to label this. You have the mass, you have the specific heat, and you have the change in temperature. So what this negative sign means here, it means that the amount of the heat has been given to you. I'm sorry, the amount of the heat that has been released. Now, how do you know specific heat is given to you or not? Specific heat has a unique unit. Unit is either joule per gram degree Celsius or is calorie per gram per degree Celsius. So if the question says calculate the heat, then they should give you the specific heat. If they say what is the specific heat for this metal or other, then that means it's unknown. Then you have to find it out. Okay. You had a lot of questions about this. I mean, not you expressing the questions because you only gave me one question to solve the other day. But when I looked at the assignment, it's given few questions regarding the reaction and then the water and the bomb calorimeter. For the calorimeter, you are using heat capacity. So when you use the heat capacity of C, the only other item you need is the delta T, C delta T. For water, you are using heat and a specific heat, the heat absorbed by water, heat absorbed by specific by the calorimeter. For the calorimeter, because it's an object, they don't use the mass of this because then it's going to get more complicated, or at the same time the mass is they use only one calorimeter and that the mass doesn't change. So from problem to problem they don't have to change the mass. It's just that one calorimeter. So what they do, they give you heat capacity. Remember, based on definition for heat capacity, it says is for an object, for the bulk, for the quantity of something. So you have to find the heat capacity would be given for calorimeter, or is the question. Okay, if it's question, everything else must be given to you. And then Q for water, you already know that Q for water is mass, specific heat, delta T. So I'm going to put these dots here. That means you are multiplying these by. So this is the, and if you label this water, H2O, H2O for all, H2O, then you know this is Q for H2O. Okay. For bomb calorimeter, we are using C times change in temperature because the heat capacity will be given to you. So if you know these simple formulas, you can answer many questions. The delta H is about equal to the heat of the reaction. It's not exact the same because of the constants that you are using for calorimeter and all that. So, but for practical purposes, we are using delta H as the Q. At the pressure would be constant, so we are going to, let's look at one example that I have here. 1 gram of sample of hydrazine is burned in a bomb calorimeter containing 1200 grams of water. So I'm going to label this because if you don't label it, like usually you should have like a table for data and you label your numbers. If you don't label your numbers, then you don't know what you have. This is the M for H2O. So we have the mass for H2O. This is the mass of the sample. Then we have temperature change. So it didn't give you initial temperature and final temperature. It gives you the change in temperature. Remember, change in temperature for water and change in temperature for calorimeter is going to be the same because water is inside the calorimeter. So change in temperature counts for both water and for calorimeter. So I'm going to say this H2O equals to change in temperature for calorimeter. What should I name the calorimeter? CM, calorimeter. So this is for calorimeter, is not the centimeter, okay? Calorimeter, I'm just abbreviating. So we have the change in temperature for both. we have the mass for water, we have the heat capacity for calorimeter is given to you. Now, what are we trying to find? We are trying to find the Q for reaction. Q for the reaction is going to be Q for water plus Q for calorimeter. And the Q for calorimeter, just going to say, is called the bomb calorimeter, so we're just going to call it bomb calorimeter. What should I replace here for the water? I need the mass for water, which is the 1200 grams, times a specific heat for water. I'm going to use, I don't know, should I use in calorie or should I use in joules? If it's joules, it's going to be 4.18. So for water, we have that number. Is a constant number. Okay, so you memorize it, and whenever you need it, you use it. 4.18 joules per gram per degree Celsius. So when you write the units, then you can cancel your unit also per gram degree Celsius times change in temperature, 3.54 degrees Celsius. You see, when you cancel these units, degree Celsius is going to cancel with degree Celsius, gram would cancel with gram, and you end up with joule. Plus the heat that is coming, it was absorbed by the calorimeter. We said we are using C, H2O be negative. No, because the temperature is increasing. The temperature is increasing, so the delta T value was positive. The temperature has increased. If you want to use the whole thing as a negative because it says heat has been released, yes, you can use the whole thing as a negative. So then you have to put both of them in a parenthesis and put, say, negative, because we know in this reaction it says that the heat has been released, or how much heat is being released. Is a combustion reaction. When it's burning, is going to release heat, because this is by convention is not a negative sign. That means it's less than 0. Okay, so plus for bomb calorimeter, I had the formula in previous slide, and it was a C times delta T. The value for C is given here. This is the C for calorimeter. Delta T is the same thing here. So you are going to say 840 times, that's the joule Celsius, degree Celsius, and joules per degree Celsius. And then this is 3.54 degrees Celsius. So we need to cancel the units here also. Degree Celsius is going to be canceled with degree Celsius, and joule is going to stay. Now, you have to do this multiplication. You multiply these two numbers, and you multiply these three numbers, and add them together. And when you add them together, that is going to be the total heat in joules being released. When you have that number, go back to your problem. It says it's for 1 gram, and then it's asking for 1 mole. So if you find this value to be, value to be here, 20.7 kilojoules, if you find that value, this is a simple math. You don't expect me to do all this, you use your calculator. You find this number, you find this number, add it together. If it's a huge number, then you divide by 1,000 to change from joules to kilojoules, and then you have this number. So when you have this number, this is for 1 gram. And if it's for 1 gram, you want it for 1 mole. How would you change it for 1 mole? Then you are going to change it for, so if this is joule per gram, to convert to per mole, you're going to multiply by the molecular mass for N2H4. Nitrogen is 14. 14 times 2 is 28. Plus 4, that is going to be 32. So it's 32 gram per mole. Times 32 gram per mole. So you are going to change the joule per gram to joule per mole. So you multiply the number by 32 to get the value per mole. Heat has been released because the temperature went up. Okay. Any question about this? So for you, in order to answer this question, in order to do all this, all you had to know was that Q equals Q for water, Q for the reaction is Q for water plus Q for the calorimeter. And what else did you need to know? You need to know the formula for Q for calorimeter, which is C times delta T. And you need to know the Q water, which is the mass times specific heat times change in temperature. And I always said that I don't look for anything. Yes, you divide by 1,000 to change to kilojoules. When you are dealing with numbers too high, like higher than 10, working with them at the lower, greater scale is easier. That's why you know about the scientific notation, you know about conversions and metric system. So when you express to the kilojoules, so if it's joules, this is the joule. The value for joule is going to be 20,747 joules. If you convert to kilojoules, you divide by 1,000 to get to 20.7. So you just move the decimal by 3 places. If you express this in joules, this is going to be 664,860 joules per mole, and that's okay. If it's a multiple choice question, if you don't see that, you see this kilojoules, then you just have to grab it right away. That yes, that many joules is same thing as 664.8 kilojoules. So it's not a it's not challenge. It shouldn't be challenging for 1046 to get that. So you see how easy all of these. You just had to know this formula and know that when you are using a specific heat, so you see when you are using a specific heat here, that is for 1 gram. Then you have to change that to, and if you were using, that's per gram. So even if you use like 5 grams here, still the Q is for the 5 gram. Then you have to see how much is going to be for 1 mole if the question is for mole. Okay, another example is asking for the heat capacity of, we have the heat capacity, what is asking here, 1 gram of the sample is burned. So we have the mass of the sample that is burned, and heat capacity for calorimeter is given to you. This is the C. The mass for water is given to you. This is mass for H2O. That's what you need. I put 2 examples so you could see that they are both using the same formula. Same formula is used. As long as you know this formula, and then you know when there is a calorimeter involved in the reaction and water is involved in the reaction, then you could just say, okay, I'm using this formula, and know the formula for Q for water separately, know this, and then plug in numbers and simple math, do rearrangement, find the value. So it's the temperature of the water at 25 degrees after the reaction is final. This is given to you. So you have the TI and you have the TF. You don't have the delta T. So what you do, you just calculate your delta T is 33.2 minus 25 and whatever number that is, I think it's 8.2 degrees Celsius. That's your delta T. So you have the delta T. And what is the value for Q for the combustion? Okay, for combustion of 1 gram. Is there anything challenging about this problem? Any questions about it? Should I read the solution? This solution is provided in Newton. Yes.
Will these examples also be listed when you do the recorded session that we can refer back to?
Yes, everything is recorded. Your question, your voice is recorded now too. So the session is recorded.
No, okay. Because I think I have questions, but I just want to try to work it out a little more on my own before I can.
I mean, the best thing, why I'm bringing these examples from Newton and with the explanation is okay. Don't worry about, I mean, you didn't learn how to bike without falling. You didn't learn how to swim without, drinking some pool water. You have to try it yourself, because when you try it yourself, you gain the confidence. You see, there are limited number of formulas that you have to memorize those formulas, and then is the application, just plugging in those numbers. Yes, you will see these problems is going to be my handwriting, everything is going to be recorded. My voice, your voice is going to be recorded in the session when you go back and look at the recording for this session. So you can see how it's done, and then you do it yourself. You can make mistakes. That's the good thing about Newton. I don't know why I still have few students who didn't purchase it. They don't look at the consequence that if you don't, the syllabus, the announcement for this quiz, when you register, it says we are using Newton, and now your grades are based on the Newton. So if you make a mistake, it's going to, and use those more information, some of them, I mean, if one doesn't have the video, the other one is going to have the video. It's going to show you how to do this calculation. And I'm here also to help. If you tell me like this question, this is my question, I'm going to pile up all those questions. And then when we have office hours, when we have meetings, I will bring it and I'm going to use the surface and explain it. So please do not be intimidated by chemistry. Please do not be afraid of Newton. Newton is there to help you. I would not change the course setting to Newton if I didn't see the benefit. I am teaching 2 other classes. It takes only 1 unit for you to perfect with the Newton, and then you would love it, because it's going to teach you what you didn't learn in general chemistry 1 as well. Get anything that you need, or think about the problem solving. If you don't know your ingredient, are you going to start cooking? Or if you want to cook something, you want to first find out what you have, right? If something is missing, you want to find that, buy it first. So if you know this formula, Q, I'm sorry, I'm repeating the same formula, that is Q water plus Q calorimeter. And you know this one requires mass of water and a specific heat for water and change in temperature for water. Then you try to find it. It's just to, try to find it in the problem. Where is this given? Where is this given? Which one refers to delta T? And then this one. So I hope these 2 problems at least help you to how to organize your data before you start problem solving. But there is one condition: you have to know your formula. By solving one problem in Newton, you are going to get know the formula, and then it continues with the same type of problem until you master it. Okay, just look for more information. Now, I'm not gonna spend more time on discussing. I hope I answered your question. Now we are burning 5 grams. If you burn 5 grams mass of water, and there is a 10-degree increase. So what is this? Is this a Ti, Tf, or delta T? That is a delta T, right? So if I label it, it's going to be when 32 kilojoule is released. The problem or the heat capacity is given by the joules, so you cannot use kilojoule. So you have to change this to joules. So it's going to be 32,000 joules. Same equation again. Q of the reaction is Q of the water plus W water. That's even better. And then Q of the bomb. Okay. So we have this value 32,000 equals mass of the water 750 times specific heat for water. Because this is given in joules, I'm going to use the 4.18 times change in temperature is 10 plus C times 10. C times 10. So how would you find the value for C? That's easy, right? That is easy. Does anybody agree with me? If you know your formula and you can read the problem carefully, you can find your unknown, what is looking for. So when you are solving problem, you look what is given, what is looking for. What is given? Mass for this sample is given, and then the 32,000, perfect question. Here is telling me that I have 32 kilojoule heat is released. So I read this question, heat released in a reaction, that is Q for reaction. Okay? So you have to read these words like very carefully. It says at the beginning at least, when it says 32 kilojoule of heat is released, that is the Q of reaction. But since it's kilojoules and my units for the Q of the water and Q of the other one is joules, then I have to change my kilojoules to joules. How to change to kilojoules to joules? You multiply by 1,000, so you have to convert it. Some informations are given directly, others are given indirectly. Like sometimes delta T is given to you, other times initial temperature, final temperature is given to you, then you have to calculate. Sometimes joule is given, is asking for kilojoule. Sometimes kilojoule is given and is applicable to change that to joules. Okay, any question about this problem? So basically what you find here, that's the value. You find that value, and then you subtract that from the 32,000 or bring it to the other side. And then that would be C calorimeter times 10, because that's what we have for the second part. Then you find this value that is equal to C calorimeter times 10. You divide by 10 to get the C calorimeter. A 10-gram gold ring with a specific heat. So a specific heat is given to you. C can be joule per gram degrees Celsius or kilojoule per mole, whichever they give you. C, if that is the heat capacity for calorimeter, is joules per degree Celsius. And kilojoule per mole, yes, that could be a question also. But if it's kilojoule per mole, first you have to find per gram and then convert to mole. Or you find it for the 5 gram and then you convert to mole. So you have to see how many moles you had that you did the calculation for. So if you forget how to go from mole to mass to mole, have to convert from joules to kilojoule or calorie to kilocalorie or joules to calorie to joule. Those are the problems that Newton is going to pick up, that you're missing that, and is going to give you a problem that it helps you with that conversion and understanding the units. Okay, this is a different type of this is a different type. This is like a two system, and you have a hot object and cold object. So you have a ring that is at 24 degree and then is placed in calorimeter with 118 grams of water at 1 degree Celsius. What will be the final temperature? Okay, for the final temperature, we have to find the delta T. We have to find the delta T. So we have to say the heat lost, okay, Q lost by gold equals Q gained by water. Why do I say lost by gold? Because we went through definition for heat first. It always goes from hot to cold. So gold is at 24 degree, water is at 1 degree. So gold is going to lose heat, water is going to gain heat. Law for conservation of the energy here applies. The heat lost by gold is going to be equal to heat gained by water. The heat loss has a negative sign by convention. So even if you don't use this negative and at the end just understand that this was the heat lost, or if you got like negative for the other side, you know where it's coming from. Numerical value should be fine for you. Okay. So what is this is the object. So what would be the calculation for heat? Is the mass times the specific heat times change in temperature. So you have the mass. You want to make sure that this is this for gold and gold equals mass specific heat times change in temperature. This is for water. Same thing, right? H2. Now, what is given to you? I'm going to just change the color here. Tell me what is given. Is mass for AU given to you? Yes, right? We have 10 grams of gold. Is the specific heat for AU given to you? Yes, is given. Is the change in temperature given to you? Yes, is given because I have the 24 to begin with and now it's reaching to, actually is not given to me. So delta T is not given, only the initial temperature is given. So I need to find the final temperature. Okay, so I need to find the final temperature. So delta T is missing here. So I'm going to leave it there. And then I have mass for water is given to me. Yes, a specific heat is given to me. So this is the TF minus TI for gold. TI is given to me is 24. TF is not given. And then for this one is TF is not given to me. TF minus 1. TI is given to me. And the rest is not chemistry, it's math. Right? How to rearrange it, which ones you have, you plug in the numbers. You have one unknown, and that is the TF. So you are going to find this value on this side for the TF, and then you find it for, then you are going to solve the problem based on the value for TF. So you have to multiply this, each one by TF and TI, and then you have the number. So the rest is math. And the solution is provided here for you, how to get, in case if you need help with the math part. So you bring the like terms together, then you take these to the other side. Every time you take something to the other side or bring this side, the sign is going to change. So when you bring this to the other side, it's going to be negative. This one to the other side will be also negative. So you get your new numbers together. Okay, heat of the reaction. Delta H for most of the reactions, it's given. So what is this? Showing that the heat of the fusion, we have heat of the vaporization is given here. Heat for this reaction is given. So when you have value for delta H, that means this is the heat for a process or reaction, a specific reaction. And this 56 is only for 1 mole, and that can change to, if it's 2 mole, then you have to change it. The standard enthalpy of formation is used for the elements, for the compound made from elements. If you have element in free state, like delta HF for O2 in gas form, is going to be 0. Delta H formation for O3 is not 0 because oxygen in nature appears as O2, not O3. So it's going to be 142. And this value, you don't have to memorize it. It will be given to you unless is a question that everything else is given and you have to find one. Delta HF for carbon in graphite, that they take this one as the standard, is 0. Any other form of carbon, like diamond, is going to have a value. Okay, so element, the way they appear in nature, delta H formation is considered by convention to be 0, and then they calculate the difference in energy when they change to a compound. And then you have delta H formation. These are constant numbers. I mean, they will be provided to you unless everything else is provided, and that is the question. Enthalpy for reaction using the delta H formation, delta H of product, delta H formation. So let's say I have, let me see if I have a formula. So let's say if I have one of these, 1 and 2, and this is a 2, and this is a 3. So based on this reaction, if 1 mole of A with 2 moles of B with combines, it's going to give me 2 moles of C and 3 moles of D. Now, the value for delta H formation for each of these needs to be given to me in order for me to find out how much heat is going to be released. Sometimes it could be 0, other times it's going to be non-zero. So if it's element, it's going to be 0. So it's always delta H of product, delta H formation of all products, minus delta H formation for all reactants. And when I say all, what does it mean? I'm counting for each of the product times the number of moles of that product, because delta H formation is for 1 mole. You need to know that definition. We talked about this on Tuesday also. Delta H formation is only for 1 mole. So if you have 3 moles, you multiply by 3. If you have 2 moles, you multiply by 2. And each number is different. Delta H formation for D is different from C and A and B. So delta H for the reaction, delta H formation for all products minus delta H formation for all reactants. What does Hess's law says? Hess's law says it doesn't matter how you get there, only where you start and where you end. So what does it mean here? You can use the enthalpy of 2 or 3 other reactions in order to find delta H for one single reaction. Let's say if we have delta H for these 2 reactions, how can we find delta H for this reaction? Hess's law. Now we want to end up with this. So we want to rearrange this 2 reaction. And I said already, if you reverse it, the sign will change. If you double it, the value would double. If you divide by 2, the value would divide by 2. Now, I want to come up with this reaction. How should I change this? I know in this reaction, I have carbon on the reactant side, so I'm not going to reverse this reaction. I'm going to keep it the same way it is, okay? But it's asking for 2 carbon. I only have 1 carbon here, so I'm going to have to multiply this by 2. So I have to multiply that by 2. Okay. Then oxygen is on the reactant side, so the oxygen is going to be on the reactant side. I'm going to keep this on the reactant side. So I'm not reversing. I already said I'm not reversing this reaction, but I have to multiply by 2. For this reaction, the CO2, it doesn't appear there on my final reaction. So what should I do with this CO2? If the CO2 is on the reactant side, And I had, after multiplying this by 2 as on the product side, when I add the 2, it's going to cancel from each side, right? I have 1 O2 here, but when I multiply this, let me apply the 2. Now I have 2, 2, and 2. Okay, so if I add these two reactions, how I'm going to add it? This is how you add it. You draw the arrow line first, then you add the reactants, all of the reactants and write in the reactant side. So you would say 2 carbon plus 2 O2 plus 2 CO2. On the product side, you write all your products after, if you add or multiply or whatever you have done. You say 2 CO2 plus 2 CO plus O2. Then simplify it. You don't have to simplify the equation, right? Like terms would cancel from each side. CO2 would cancel from this side. And then you have 2 O2, you have here 1 O2. One of the O2s is going to cancel with one of the O2, and you end up with 1. Then it gives you the reaction, desired reaction. What did you do to this? You multiply by 2. So this has to multiply by 2. So you multiply these number by 2 and add to this number, and that would be the delta H for this reaction that you were looking for. So that's Hess's law. But the trick is not the trick. Like, this is like you could have like good imagination. You could do like a mental math. You could do whatever you like to decide, should you reverse a reaction? Should you multiply by a number? Look at what you're trying to end up with. And if you're trying to end up with this, then you know that carbon has to stay on the product side, on the reactant side. If the C had appeared on the product side, then you had to reverse this reaction. So you want to find this. Can you tell me if I should reverse the reaction 1 or not? Should I reverse this reaction? Can you hear me? Just say yes or no. Should I reverse it or keep it? First reaction, should I reverse or keep? Can you hear me? Why should I reverse it? This is my desired reaction, right? This is my desired reaction. Graphite appears on the reactant side. This reaction shows the graphite on the reactant side. So, Jeffrey, I need to keep it. Keep it because C is on the reactant side under my desire. This is my desire. This is what I want to end up with. Okay, so I'm going to keep this same. I have 1 carbon. There's 1 carbon here, so I'm not going to multiply by anything either. Second reaction, I have S on the reactant side. This S is on the reactant side. Do I have to reverse it? Yes or no? No. Okay, no, I don't have to reverse it. I have 2 S here, but in only 1 S. What should I do? Do I have to multiply by 2, right? So I have to multiply by 2. Why do I have to multiply by 2? And if I'm multiplying by 2 the reaction, I'm also multiplying the delta H values also. So if I multiply, I have to multiply this by 2. 2, 2, 2, and then this is going to be times 2. Okay, CS2 is on the product side. CS2 is on the product side. This is on the reactant side. I can only play with these reactions. I cannot play with the final reaction or desired reaction. So I have to reverse this. And it's only 1, so I don't have to multiply by a number. I only have to reverse it. So when I reverse it, this sign is going to change to positive sign here. Positive. Okay. I change it to, it's going to be positive. And then this is going to change. So now I have a new reaction. My new reaction is going to show the CO2 and SO2 on the reactant side, and the CS2 and 3O2 on the product side. Then I add. So you see that you have the multiply by 2, and then this one has been reversed. Now, when you're adding, you draw one arrow, and this is your arrow sign here. Anything that appears on the reactant side should go on the reactant side. Anything appears to the left of any of these arrows, it should go on the product side. You can also simplify it before you add, or you add everything and simplify it. Whatever you want it, you feel better. Why did I reverse it? Why did I reverse it? Because my CS2 here is on the reactant side, because I can play only with these numbers. CS2 is on the reactant side, but desired reaction, which this is what I want to come up with, is on the product side. So I have to reverse this reaction to bring this one to the product. Okay. Then you are going to come up with the delta H value that shows the total of delta H for all three reactions after the changes that you made to your reactions. Why did you make changes? Because you wanted to add up to this desired reaction. This is the Hess's law. Okay. To C6H6 is burned in air to produce carbon dioxide and water, so you have to balance the equation first. You write the equation and you balance it. It says burned in water, burned in air. You don't put air here. You know that is a combustion reaction. It requires oxygen. So you have to write the equation and then you balance it. Okay. Then you find the delta H formation for water. You find the delta H formation for carbon dioxide. You have delta H formation for O2. We already know is 0. So you don't have to worry about it. Or you just know that is 0 is going to make your steps less. And then delta H formation for standard enthalpy formation for benzene is 49. This number is given, 04. But these numbers you have to find from tables. You don't have it, you have to find it from the tables. Or it will be given to you. If it's an exam question, it will be given to you. If it's a homework question, you have access to tables, and you had that numbers, or they're all the same. As long as you see this sign, delta H formation for water, you can search for it. Okay. So delta H of the reaction is delta H formation for products minus the reactants. So here is your first product, but you have 12 of them. Second product, you have 6 of them. The D and delta, please, is the same thing. It's just when it converts, it just changes when I bring it up to the calorie. And then you see the oxygen is not written here because we know oxygen is 0. The rest is math. And these are very simple, but very easy to make mistakes. If you forget to put 12 here, you're not going to get the right answer. If you forget to put the 6 here, you're not going to get the answer. When you find this, okay, when you find this number here, that's based on this balance equation. This is because delta H is a reaction specific. And your reaction must be balanced before you find the delta H. Now, when you find the delta H is based on this. The question is asking for 1 mole per mole. Then when you find this value, you divide by 2 to get it for 1 mole. Because delta H is reaction specific. Delta H formation is, what is downloading now? Okay. Delta H formation is for 1 mole, but delta H reaction is per balanced equation. So it's not per mole. You have to Okay, thermodynamic. When you say thermodynamic, that means you are dealing with delta H, which you already learned how to calculate for the reaction. You learn about delta S, which is entropy, degree of disorder, and you learn about delta G, which is the free energy. Delta H for the reaction is the H formation, sum of H formation of products minus sum of delta H formation for reactant. Delta S for reaction is sum of delta S formation for products minus sum of delta H formation for reactants. Delta S, sorry. Delta S0, standard. Okay, or S entropy of the, or NS. So is the sum of the product minus the reactant. Delta G is delta H minus T delta S. And this T must be in Kelvin. Okay. So degree of this entropy, increase, decrease, what is happening? You go from solid to liquid to gas. Is going to increase. S is going to increase. Why is increasing? Because degree of disorder is increasing. They're all sitting down like polite, whatever, like fixed, no motion. Here molecules are moving, here molecules are flying. Degree of disorder is much greater. If you go from 1 mole to 2 mole from the reactant to product side, S is increasing because more people, more degree of disorder. If you go from solid to gas, of course, is going to increase. So these are the concepts that you have to understand what is happening. And then the delta H negative sign favors spontaneous, but it doesn't mean that it's spontaneous. Positive, it favors non-spontaneous, but it doesn't mean that it is non-spontaneous because there are two factors that is going to affect the reaction being spontaneous or not. Is not delta H alone, is the delta G, that if is less than 0, then we have a spontaneous. For delta G greater than 0 is non-spontaneous reaction. Someone had question about the free energy is the combination of delta H and delta S, and negative sign for that means is spontaneous. So we talked about this already. I'm not going to repeat what I said. The spontaneous, in the spontaneous process, degree of disorder is going to increase because the universe, the entropy of the universe increases in a spontaneous reaction. I mean, it's much easier for you disorganize your room than spending time to organize it. And that's by nature. Okay. The entropy change, we talked about some of the factors going from 1 mole gas to 2 mole gas. Entropy is increasing, but here you have 3 moles gas, right? You have 2 and 1, 3 moles of gas. Here you have 2 moles. A number of moles of gas is decreasing, so entropy is decreasing. And delta S for the reaction is S of product minus S of the reactants. You just have to add them all up. The entropy of perfect crystalline substance is 0 at absolute 0. That is negative 273 degrees Celsius. Absolute 0. But life is not possible there. Delta G, I already talked about. Delta H minus T delta S, and this T must be in Kelvin. If delta G is 0, your reaction is at equilibrium. If it's less than 0 is spontaneous. What does spontaneous mean? It means that reactants will go to product by themselves. Non-spontaneous, it means that reactants do not want to go to product unless you push it how you push for reaction, you bring catalyst, or you will have to increase the temperature. G stands for free energy and S stands for entropy. So Gibbs free energy, that is G. That's the overall thermodynamic value that is going to tell us if the reaction will be spontaneous or non-spontaneous. G depends on H, delta H, and it depends on delta S. And this is the equation. Delta G is delta H minus T delta S. This is entropy, and this is enthalpy. The value for delta G, it shows if the reaction is spontaneous or non-spontaneous. If we have the value, see, we have the value for delta H. We have the value for delta S. What temperature reaction will be spontaneous? Okay, for reaction to be spontaneous, the delta G value must be less than 0. If we say delta G is equals delta H minus T delta S, and then delta G value when it's 0 is at equilibrium, right? At equilibrium. What does equilibrium means? Equilibrium means reaction goes forward and reverse with the same rate. So when delta G is 0, delta H minus T delta S is 0. That means delta H equals T delta S. So we find that T by dividing delta H over delta S. So you need to know the concept in order to answer this question. You need to know that when delta G is 0, reaction is at equilibrium. Any temperature higher than this, it will be spontaneous. Any temperature lower than this is going to be non-spontaneous. Why I'm talking about higher temperature? Because this reaction is the endothermic. Higher the energy is going to go faster. So at temperature higher than this temperature, this reaction is going to be spontaneous. So it's understanding of the delta G formula. So if the temperature is 702 Kelvin or higher, is going to be spontaneous. When you're adding or subtracting, another point that you have to be careful with, especially for multiple choice questions and forever, if you're adding, you cannot say I have like $10.05, that's going to be $15, right? It's not going to be $10.05, $15, because one is dollar, the other one is cents. Your units must be like before you add or subtract. That is coming from math, 1045, other practices, and I'm not telling you should know before, I'm reminding you how to do it, okay? This is a kilojoule. For delta H values are kilojoule, delta S values are in joules. Be careful. When you are adding here, the units must be like. Both of them kilojoule or both of them joules. Have to go from joule to kilojoule, divide by 1,000. From kilojoule to joule, you have to multiply by 1,000. If the delta G value is given for every reactant and product, you could also use the delta G reaction equal sum of the delta G0 of products minus sum of the delta G0 of the reactants also. But that's the condition that these values are given for reactants and for products. If it's 0, that means your reaction is at equilibrium. When you say sum, the total number of moles. So if for the value for oxygen is 0, then it's going to be 0. If it's a different number, it's going to be, the numbers are to be provided to you, each individual numbers for exam. If it's not exam, is expecting that you search it up or have a table in the book. The tables in the book is going to have the those values. So you have to find those values. But setting it up, it's the bracket, 2 brackets with the minus sign in between. The first bracket, you have all your products. The second bracket is for your reactant. And inside the bracket, so when you set up any of this delta H, delta G, delta S, you put like bracket minus a bracket. And inside the bracket, you're going to put parenthesis plus parenthesis. If you have 2 products, and here you have 2 reactants. So this is the product, this is your reactant. Then you fill in. Okay, the first one is the number of moles of product, which is 12, times this value. Plus, second one is the number of moles of second product times the value for second product. And then this format stays standard. Okay, the delta G value could be positive or negative, so be it. You know how to multiply positive or negative, and you can add when it's positive or negative too. So if you had these 2 in the parenthesis, it would probably make it easier for you to do this one. Then you are using the PEMDAS. You are going to take care of the parenthesis first. Okay, I want to see one thing here. Okay, questions? Questions? What makes the reaction, under what condition reaction would always be spontaneous? If you have negative for delta H, positive for delta S, your reaction would always be, yes, those numbers will be given for the exam, but for the homework, you have access to book and you will find them in the table of the chapter. It's provided in the book. So reaction will be always spontaneous if both of them are favored. Negative sign for delta H means exothermic reaction. That means it's favored for spontaneous. A positive based on the second law, thermodynamic law, is that positive delta S is favored. So if both of them are favored, it would always be favored. If both of them are not favored, then it would never be spontaneous. And if one is favored, the other one is not favored, then you have to look for the temperature. For endothermic reaction, high temperatures are favored. Exothermic reaction, low temperatures are favored. When your reaction is at equilibrium, delta G value is 0. And then delta H, this is at equilibrium. Delta H is going to be equal to delta T delta S, and the value for T is in Kelvin. Another formula which is going to relate the equilibrium constant to delta G value is, if you have the delta G 0, R, T, L, and Q. What is Q is concentration of the product over concentration of reactants raised to the power of the coefficient. So you may not use it for this chapter, but when you study equilibrium, then you are going to use this formula later. Okay. The Q versus K. Q is concentration of the product over concentration of the reactant. K is concentration of product over concentration of the reactant at equilibrium. That's the only thing. So Q and the difference between Q and K. If the delta G value is 0, that means 0 equals delta G0 minus RT ln K. So K means equilibrium, okay? Concentration of product over the reactant at equilibrium. So again, this formula, you may not get problem with this chapter, but you will get it later. Okay, 11 o'clock, and I'm going to stop the recording here. Do you have a any quick question? No questions? If you go under Blackboard Collaborate and click on recording, you will find the recording. I labeled that July 2nd, so hopefully you will find it as a July 2nd. Okay. You're welcome. Thank you so much. Your lab situation, we received an email from you and our lab professor. You received email from me. I didn't know that you got email from me. For your lab situation, you're welcome. You're welcome. For the lab situation, I create a course, a lab course, instead of going with the HOL, which is the hands-on lab. That will cost like $190. Now you have to, you don't have to purchase that because it takes, that wasn't the reason, only reason, because it was coming late. If you order today, it takes like 2 weeks for it to get to your house. And by that time, it was too late to start the lab. So I suggested them to use my course. And in my course, I'm doing the experiment, recorded experiments. So you should have access to that course at this point. When you go there, you look for the videos, you see the recording. I only do the experiment and I show the observation. You record and you follow me like step by step in order to get your data. And then when you get your data, I'm not your new professor. It's going to be Professor Gillings, Aaron Gillings. No, they only use my course. I'm not your new professor for the lab. The ebook for the lab, you will have the copy of the first experiments already in the. You will have the copy of the first experiment that is going to set you up for today and for Friday lab. For next week, you will get a copy, and as soon as the ebook is ready, you will get an email with the ISBN number. And if the ebook is available and you don't purchase it, you won't be able to see the assignments because the lab is not complete. The course is not complete without the ebook. The ebook costs like $50, like 25% of what you have to pay for the HOL anyway, but it's very helpful because it has everything that you need. Which video? Lab video or lecture video? Camelia, is that lab video or lecture video? The lab video folders, you will find the folders. I don't have, when you go in there, your course, on the right side, you have the classworks, coursework folder. Someone's mic is on.